Hi, welcome to this module. In this module, we will see a non-inverting Schmitt trigger circuit. Now, if you remember in the inverting Schmitt trigger circuit, we have seen how the hysteresis voltage is dependent on the regenerative feedback, right. So, here if I want to understand how the non-inverting Schmitt trigger circuit works, then what are the parameters that I have to look for, right. So, let us see how we can understand the non-inverting Schmitt trigger circuit. As you can see here, right, the input voltage is applied to the non-inverting terminal. There is a regenerative feedback, positive feedback, and the hysteresis characteristics of this particular circuit is shown here. Okay. So, the relation between input and output voltage, if I want to find a relation between output voltage and input voltage, then it can be given by V O by V I equals to 1 by beta divided by 1 minus 1 upon A O beta, where beta is nothing but R 1 by R 2, beta is my R 1 by R 2. And let us consider the same things that we have considered for the inverting Schmitt trigger, where first is mode of A O into beta is equal to 1. So, in this case the circuit becomes an unstable as an amplifier and its output saturates. In case of mode of AO into beta greater than equal to 1, the region of operation of this circuit becomes a regenerative comparator and output is stable only in two stages, plus VSS and minus VSS, right. Third, as mode of AO into beta is greater than 1, the output voltage is no longer related linearly to the input, and in this mode the output voltage behaves as digital wave and shows two stable states. This is similar operation if you understand inverting Schmitt trigger circuit. But what are the changes? There are very few changes in terms of only circuit diagram. So, when the input is large positive, output saturates to plus VSS. As the input is decreased, the output remains at plus VSS until input reaches to beta VSS. The device enters into regenerative feedback mode and the output changes from plus VSS to minus VSS, right. So, as the input is increased, the change in output can be reflected if the input is increased above plus beta VSS, right. So, what is the hysteresis? Hysteresis is plus minus beta VSS, and on either side of origin there is a hysteresis, total hysteresis of beta VSS minus beta VSS, it is like 2 times beta VSS, right. So, this controller can be used as an on off controller. So, at positive saturation what will happen? VO equals to VSS, right. If it is saturates, it can go to the maximum value which is plus VSS. Voltage at positive terminal V plus equals to minus VSS minus VI divided by R1 plus R2 into R1. When I say maximum VSS, does not mean that it will reach to plus 15 volts. Suppose I apply plus 15, I apply minus 15, you guys know that if this goes saturation, does not go exactly plus 15 volt, it is less than plus 15 volts, and how much is it is your homework. It never reaches to plus 15 volts, alright. So, understand that when you talk about saturation, it is not exactly plus VSS, it is less than plus VSS or less than minus VSS. Okay. So, we have V plus equals to minus VSS minus VI divided by R1 plus R2 into R1 plus VI, which is equal to R2 by R1 plus R2 in the bracket VI minus R1 by R2 VSS bracket over. So, if V is positive or input voltage is positive and magnitude is greater than R1 by R2 VSS, what will happen? Then V plus will be positive and output will switch to VSS, right. That means, if my Vi input voltage is positive and the magnitude is greater than R1 by R2 into VSS, then my V plus will be positive and output will switch to plus VSS. So, VUT equals to R1 by R2 into VSS, right, which is my upper trigger point. At negative saturation, this is at positive saturation. At negative saturation, my VO equals to minus VSS, right. So, in this case what will happen? Voltage at positive terminal V plus equals to VSS minus Vi by R1 plus R2 into R1 plus Vi. So, if I solve this, I have R2 divided by R1 plus R2 into Vi plus R1 by R2 into VSS. Now, if my Vi is negative and magnitude is less than minus R1 by R2 into VSS, what will I have? I will have V plus will be negative and output will switch to minus VSS, right. So, my output is switching plus VSS to minus VSS when my voltage Vi is greater than R1 by R2 into VSS or is less than minus R1 by R2 into VSS, right. So, in this case my upper voltage was VUT equals to R1 by R2 VSS, my lower voltage is minus R1 by R2 into VSS. Thus, my hysteresis voltage will be V hysteresis VUT minus VLT, VUT is R1 by R2 into VSS minus R1 by R2. So, we have written like R1 by R2 VSS minus of R1 by R2 into VSS. This will be nothing but plus 2 times R1 by R2 into VSS, and what is R1 by R2? R1 by R2 is our beta. So, 2 times beta VSS, right. This is what we call here that the total hysteresis of 2 times beta VSS, right. So, this is how your non-inverting Schmitt trigger circuit works, right. In case of inverting and non-inverting circuits for Schmitt trigger application, we will have the output which is in on and off condition. So, let us see if I want to perform an experiment, right, to design the Schmitt trigger circuit, then non-inverting Schmitt trigger circuit is shown here, where you have to connect the circuit as shown in the diagram. Then you have to select the resistance R1 and R2 and calculate beta into VSS, apply sine wave at the input voltage and observe the DC transfer characteristics from the oscilloscope and compare with the theoretical results. Vary the regenerative feedback and observe the variation in the hysteresis. So, the observations are still the same. You apply a regenerative feedback, you look at the hysteresis. Alright guys. So, what we have done here is we have understood non-inverting Schmitt trigger circuit. Now, to design the circuit using multisim, again we will ask our friend Sitaram who will show us how to perform the experiment using multisim.
Now, we are going to work on non-inverting type Schmitt trigger. When it comes to the circuit, if you observe, there won't be much difference between inverting type of Schmitt trigger and non-inverting type of Schmitt trigger, but only difference is that rather than giving an input to an inverting terminal, the input will be provided to the non-inverting terminal, but the feedback should always be a positive feedback. The reason is, in Schmitt trigger the op amp has to be operated in saturation mode. So, it is also some kind of a comparator, but comparator will only have a single threshold. If input is higher, it goes to plus VCC, if input is lower than the threshold value, it goes to minus VCC. But whereas Schmitt trigger, you can select when to go high, when to go low based upon the resistors that you choose, and you can decide the width of your hysteresis or the lag between on and off of your system. Now, as we have already seen, as a professor already discussed about non-inverting type Schmitt trigger, we will see what experiment that we are going to do, how the connections of an non-inverting type of Schmitt trigger, what is the difference between inverting and non-inverting when it comes to circuit connections, everything. Then later on we will use the simulation. First one is the theoretical. We will take different resistors values, we will calculate beta, and we will also calculate lower threshold value as well as a higher threshold value for the chosen resistors, and theoretically we will calculate what is the higher threshold and lower threshold, then we will compare with a simulation, we will analyze the relation between the input and the output, how the output is varying, which depends upon the change in the resistance, and we will also experimentally verify using TI kit. As we have already seen, it is similar to that of what we have seen for inverting type of Schmitt trigger too. Now, when we look into the non-inverting type Schmitt trigger circuit, we can see that the major difference is that the connection. So, as we remember, in case of an inverting type, the input is connected to the negative terminal, and this particular point was connected to ground. But in this case, it is input is given to non-inverting terminal. That is why it is called non-inverting Schmitt trigger. So, the negative terminal is connected to ground. Apart from this, everything looks same. So, when you see the characteristics, the output curve, the relation between the input and output, it was also inverted of your previous output or of your inverting type Schmitt trigger. If you recall what we have seen in our inverting Schmitt trigger circuit, when the input is greater than the upper threshold, the output will be minus VCC, right. But whereas in this case, when the input is greater than lower threshold value, the output is minus VCC. But whereas in the previous case, in inverting type, when the input is lower than lower threshold value, the output is plus VCC. But whereas in this case, it is minus VCC. And similarly, when the input is greater than beta VSS, which is your higher threshold value. So, I am saying this is called lower threshold value, I will say VTL, and this is nothing but VTH, higher threshold value. So, when your input is greater than this VTH, then the output will be plus VCC. Apart from this, the operation wise everything same. But how about the relation between the resistance and beta? In a previous case, if you recall what we have discussed, the beta is nothing but R1 by R1 plus R2, whereas in this case the beta is R1 by R2. I hope this we have professor has already covered in the theory session. Now, when we look into the experiment, what we are going to do, we will choose different resistance value. We will take TL082 in an experiment. So, it is a dual op amp that we have already seen in the last session too, and we will consider different R1, R2, and we will connect accordingly, right. And for the chosen resistance value of different R1, R2, we will calculate beta, and then we will calculate the higher threshold and lower threshold values too. Then, so for that case, what I will do is that initially we will choose resistance as 1K and 10K. So, I will say R1 is equal to 1 kilo ohm, R2 is equal to 10 kilo ohm. So, if it is a case, what is the beta value? So, as we know that beta is nothing but R1 by R2. So, the beta value is 1 by 10, which is 0.1, right. Then what about the lower threshold? So, VTL, which is nothing but our lower threshold, that is what we are doing the nomenclature for that, which is beta minus, I will say minus beta into VSS, nothing but what is our negative supply voltage into what is the beta value. So, since beta is depends on R1 and R2, and from the calculation we can see it is a 0.1 value, and we will be operating our VSS and minus VSS with plus 15 volts and minus 15 volts. So, this VSS will become 15, since it is minus VSS, it is minus. So, which is nothing but 1.5 minus 1.5 volts is the lower threshold value, right. So, similarly higher threshold value VTH I am representing as plus 1.5 volts. So, if you recall how the output characteristics of a non-inverting amplifier, we know that when the input voltage, whatever the input that we are applying, when this particular input voltage is greater than this VTH, in this case it is nothing but 1.5 volts, then we will get high, right. Then again, till what time it will be high? When our negative, when our lower threshold value VTL, if the input value, input voltage is lower than this VTL, till then it will be higher. So, in our case it is minus 1.5, right. So, when the input voltage value is lower than minus 1.5 or here minus 1.5, till then it will be higher, right, and it keep on continuous, right. And what will be this voltage value? This will be plus VCC and minus VCC. The reason why it will be always in plus VCC and minus VCC, because since op amp open loop gain of an op amp itself is almost very higher, since the op amp is also connected in a positive feedback manner, when we look into the transfer function of a positive feedback, the overall gain will be even more higher than the open loop gain. As a result, since the gain is higher, even small input voltage is enough to make the op amp to operate in a saturation region. Because of that reason, the op amp output will be always in either in plus VCC state or minus VCC state. And in this case, we have operating the op amp at 15 volts and minus 15 volts. So, that is the reason the higher value output will be plus 15 and the lower is minus 15, but when to switch on, when to switch off will be decided by the thresholds. That means, it depends upon the resistors that we are using it. Okay. Then we will take another resistance values too. We will see for a different resistance value and we will calculate. Once we calculate our lower threshold and higher threshold value, we will do the simulation of by considering the same resistance, connecting the similar way as we have seen in the circuit, and we will compare the theoretical and simulation. Once both are done, we will also look into the experimental thing. So, all three will compare and we will finish this experiment. So, now I will consider R1 as 10K and R2 also as 10K. So, when you see the beta will be 10 by 10, which is 1, right. So, VTL will be what? VTL will be minus 10 into 15, right. So, which is nothing but 1, beta is 1 minus 1 into 15, which is minus 15 volts, and whereas VTH is nothing but VTH is plus 15 volts. But since in a simulation we can easily see, because since in a simulation there are no restrictions of the input voltage, we can easily see, but this is very difficult to visualize with our experimental, because our source, when you see the maximum peak to peak value you can get is of 20 volts. So, that means the peak value will be only of 10 volts. So, since in this case we require a peak of more than 10 volts, this cannot be used in our application. So, but in simulation we will see how exactly it works, whether it is working as per expected or not. Next, what about other resistance value? I will take R1 as 1 kilo and R2 as 2.2 kilo, 1 kilo and R2 as 2.2 kilo. So, what will be the beta value? 1 by 2.2. So, 1 by 2.2 is 6.818 volts, sorry. So, 1 by 2.2, okay, we will take a calci, 1 divided by 2.2. So, 0.4545, this is the beta value. Now, what about VTH, VTL? So, VTL is minus 0.45 into 15, so which is nothing but into 15. So, 6.818 minus, so the lower threshold is minus 6.818 and similarly the higher threshold will be plus 6.818 volts, right. So, we will verify the same thing using simulation first. Now, when I look into the simulation, we will open NA Multisim. Right. So, when we see, first thing is we have to take an op amp. So, I will go to the op amp and this is analog pellet. So, in this if I look into that, you have 5 terminal op amp, I am placing 5 terminal op amp here. Now, I have to provide the plus VCC and minus VCC to the op amp. So, I will go to source pellet, here I will go with a DC voltage and I will rotate it, I will connect from here to here. right. And similarly, I need a ground, I will put a ground, later on I will connect it, and again I need one more supply voltage here to power it, the negative bias power, then again the ground, right. What else we require? We also require resistance value. So, I will take a resistor. So, should be, is it a negative or positive? So, it is a positive feedback. So, I am taking a positive feedback. Then what about negative? Negative should be connected to the ground. So, I will take one more ground, I will place it near the negative terminal. Now, where the input to be applied and where to measure the output? Input should be applied at R1 resistor. So, what I will take? I will take a sinusoidal wave. So, AC voltage I will place it here with respect to the ground, we have to measure with respect to the ground. After placing everything, I will connect the wiring. So, how to do connection? Simply wherever you want to create a wire, just go to the end tip, press left mouse click, automatically the tool will be converted to wiring tool. Then move your mouse. So, wherever there is a connector, it automatically shows the zoom out function. So, when you click it, automatically it will connect it, right. Similarly, from here just go here and click it here, and again from resistor to the positive terminal, and this resistance to this positive terminal, and the other end of the resistor has to be connected to V out. This is my V out, and the negative terminal should be connected to the ground, and the positive input bias input voltage should be connected to positive source, and negative terminal should be connected to the ground. The voltage that I have to apply is 15 volts, right. That is what we have done in the calculations too. If you would have done the calculation using 10 volts, then you can apply 10 volts here too. So, then the output will be fluctuate from plus or minus 10 volts, but thresholds will change, beta into VCC or beta into VSS. Similarly, even here. So, I have to connect negative to the negative terminal. So, that since the voltage shows 12, so I have to change with 15. Since it is a 15, since the negative terminal is connected here, that means the voltage that we are applying is minus 15 volts, right. Then, so is everything ready? Yes, our circuit is done now, but we have to do the comparison. We have to see the relation between the input and output. Until unless we connect a scope, the circuit will be working, but it is very difficult for us to visualize it. So, what we do is that I will go to this analog and annotation palette. Here we have voltage indicators or kind of a graphers, probes, those are called probes, and we can take one more probe and connect at the output voltage terminal, right. Now, I have already created the probes wherever I want to see the input and output. So, input will be in green and output will be in blue color, but is this resistance okay for me? If I use this resistance value, it is nothing but beta values of 1. So, beta into VSS, VSS is 15, then this is the second case, but right now first we will go with the first case. So, for that I will take R1 as 1 kilo, R2 as 10 kilo. So, I will change R2 to 10 kilo ohms, right. Now, what is the input voltage? When we look into the presentation, we remember that the threshold value is 1.5, plus 1.5 and minus 1.5. When we recall what is an expected output, if you remember, when my input voltage is greater than the higher threshold value, meaning in this case when the input voltage is greater than plus 1.5 volts, I should get an output as plus VCC, meaning it is 15 volts. Similarly, when the input voltage is lower than minus 15 volts or sorry minus 1.5 volts, it is a lower threshold value, I should get an output as minus VCC. Now, is my input okay to measure both whether I am getting plus VCC as well as minus VCC? No, the reason is the input voltage is below than the higher threshold value itself. Since it is lesser than the higher threshold, it will be in one saturation, it will be in plus VCC, sorry it will be in a minus VCC. We can also simulate and we can see. Okay. So, we need to apply more than threshold voltage. So, I will go peak value as 2 volts. So, I am going peak value as 2 volts and I am going to run the value, going to the grapher, yes, going to settings and change scaling it. So, here we can clearly observe that this is my input, the green color line is my input and the blue color line is my output. So, for our understanding, okay, what is the peak value? It is somewhere around 2 volts. Now, what we have to create a cursor, so that easy for us to understand. What I will do is that I will go to y axis cursor, one cursor should be at 1.5 volts, right. So, when you look into this particular point, we can see where exactly the cursor is at, right. Cursor 1 is somewhere around 1.8. So, I have to make it as 1.5, right. Oh, so it just slightly crossed 1.5. So, I will just move towards 1.5 volts. So, somewhere around 1.5. Now, other cursor should be at where? Minus 1.5, because that is the threshold that we have created. Where do I have to see? At this point. Now, I will go slowly little down, up, okay, 1.59, yes, minus 1.5, approximately minus 1.59. Now, when I see, so the triggering I will make it as a single, so that I cannot see any fluctuation. Now, when we observe it, what we have understood, when we see that the output voltage will go to plus 15 volts when the input value is greater than VTH. In this case, VTH is 1.5 volts. So, when we see, when this cursor is, when this green line is greater than C1, which is the cursor 1, we can see the output is moving to plus VCC, right. And similarly, when it goes to minus VCC, since it is not a comparator, when our input is lower than C1, it will not go to VCC. It will go to minus VCC only when the input is lower than C2 value. Now, observe that when I see the input is decreasing, sorry, this should be 1.5, yeah, this is 1.5, yeah. Now, when you observe, whenever the input is lower than minus cursor 2, which is minus 1.5, which is lower threshold value, then the output is moved towards minus VCC. So, everywhere it is happening in the same way. But what is the difference that you observe from inverting and non-inverting type? In case of inverting, this would have been in a reverse way, meaning when the input is greater than C1, I would have get minus VCC, but when the input is lower than C2, then the output would have been plus VCC. But in this case, it is a completely similar to the input, similar to the threshold. Threshold input is greater than first higher threshold, go to plus VCC, right. Now, we will go to the schematic, we will change our resistance values and we will observe whether it is also affecting for other, whether the output, expected output is same for the second case also. So, in a second case, the resistance, both resistance should be of 10K, isn't it? That is the case that we have considered. So, look into the slide, when we see that R1 is also 10K, R2 is also 10K. So, the beta value is 1. Now, the threshold is minus 15 and plus 15. So, when I go here, I will change it to 10K, 10K, oh, this should be 10K, right. Now, both resistors are 10K. As a result, the beta value is 1. Now, when I go back to the to our grapher. Now, one more important thing, what? The input value. Now, the thresholds values are not below the 2 volts, right. The peak value of the input is 2 volts, right, but the thresholds are even higher than the 2 volts. So, we cannot see that operation, right. So, in order to see the operation, what we have to do? We have to increase the input voltage greater than 2 volts, right, sorry, greater than the VTH. Now, in this case the VTH is 15. So, what I will do is that I will make it as 20 peak, that means peak to peak is 40, right. Now, the input is more than 20 volts, even the negative input is minus 20 volts. So, when I look into the grapher, Okay, I have to make it as auto, yes, auto. So, it is updated, then I am making it as a single. Now, if you observe it here, so what I will do is that I will decrease the time duration. So, easy for us to understand. Now, what are my C1 and C2? Meaning C1 is higher threshold and C2 is a lower threshold. C1 is plus 15, C2 is minus 15. So, I will set C1 as plus 15. So, you can see it at this point. So, C1 is somewhere around right now at 10. So, I will go to 15 volts, moving to 15, right, and C2 should be minus 15. So, C2 value we can see it here, right. Now, the output is as per expected. Why do not we check? Now, when we observe, when the input is greater than this value, input is greater than value, it started to change, right. But why the output is not greater than? In the previous case, if you observe, the input signal is smaller, output voltage is higher, but why in this case it is not? Because the saturation voltage of the op amp is plus or minus 15, but the input is higher than that, right. So, that is why we can see this is already at plus VCC. Now, when it is going to minus VCC, whenever the input just crossed your minus VLT or VTL, lower threshold value, then it has gone to minus VCC, right. Makes sense, clear, right. Now, we will look into other case also. What is other case? R1 has 1 kilo, R2 has 2.2 kilo ohms. So, go back to the schematic, then I am just stopping it, replace this with 1K and this with 2.2K, right. Now, do we need this value? May not be. Even if it is the case, we can visualize it. Even if it is smaller than that, smaller than the threshold values is also good enough. Now, what is an expected output? Here it will be whenever the input is greater than higher threshold. So, what is the higher threshold at this point? It is 6.818, right. When our input is greater than 6.8, approximately of 6.81 or 82, right, it will be at plus 15 volts. Lower than that value, it will be at minus 15 volts. Otherwise, it will follow in between, it will always follow the input. Now, in this case, if I see, if I run system and I will change. So, we do not need this a value, I will go with a 10 volts, peak value is 10 volt, peak to peak is 20 volts. Going back to the grapher, yes, here we can see C1 should be 6.8 something. So, I will take 6.8, slowly decreasing it, 86, and C2 is also 6.86, minus 6.8, right. Now, observe, when the input is greater than this particular value, so it started moving towards this value, isn't it? Observe, right, or track, I will see where the input is. Okay. Right. Yeah. Now, if I observe it here, when the input is greater than C1, I can see when I plot it here, it started moving to minus plus VCC, right. And when it is going to minus VCC, when the input is lesser than, see, observe, this is my C2 which is minus 6.86. Whenever the input is lower than this value, right, at this point it is started moving from plus 15 to minus 15 volts. So, we can understand that the difference between an inverting and non-inverting and the simulation is working as per expected to, as per the theoretical calculation. We will also see the same results, whether we get the same results when we do it in a in our experimental, with actually taking our op amp and connecting these resistors, providing an input and observing the output voltage, right. So, when we look into the board, when we look into the board, now we will do all the 3 test case scenarios. First test case scenario, I will take R1 as 1k, R2 as 10k, right, and I will apply input as sinusoidal signal, and we will see. So, since we have already calculated beta values, whether the output is going to plus VCC and minus VCC when greater than plus beta, VSS are going to minus VCC when it is lower than minus beta into VSS. We will see that. Now, when we come back to the circuit board, yes, when we see, so even in this case we are going to use this particular subsystem, right, similar to what we have done, and we will be using the same op amp, and we have already seen negative, positive terminal as well as output voltage, and the powering is already done here, right. Only thing is, if I switch on my power supply, if I switch on this power supply, right, if I switch on this power supply, I can provide a power to the operational amplifier, and I will be connecting, since this particular system does not have any resistors, we will be using this breadboard to connect the resistors, and in our design we are using different varieties of resistors. All the resistors will be connected here, and we will be wiring it through these jumpers to the board. We will provide input from this function generator, and we will visualize output from the oscilloscope. Now we will take 1 kilo ohm resistor and 10 kilo ohm resistor. So, 10 kilo ohm should be connected to feedback and 1 kilo ohm should be connected to positive input terminal to the input source, right. Now, if you observe, so we are connecting resistors. This is 1 kilo ohm resistor. So, one resistor should be connected to the positive terminal. So, if I see this resistor is connected with this wire jumper, this we are connecting it to the positive terminal. So, that is a positive terminal buck connector, buck stick. Now, what about the other terminal of the resistor? This should be connected to input. So, input is from the function generator. We are taking a function generator, right. The function generator will be, input will be connected to this particular point. Right. So, we are connecting it now. Right, input is done. Now, what about another resistor? Yes, we also need R2 resistor, which is a feedback. So, we will take 10 kilo ohms. So, we will take a 10 kilo, we will connect across positive terminal and the output, right. So, which is a positive terminal? This junction, this particular junction is a positive terminal junction, right. So, to other side of the breadboard, other column of the breadboard, we will be connecting this resistor, and other end we will connect it to the output voltage. Now, in this case, if I see the green color wire, this green color wire is one end is connected to the output, right, and other end we are connecting it to this other end of the resistor. Right. Now, so we made connections to the positive terminal. We also made a connection to the feedback resistor. What about the negative terminal of an op amp? The negative terminal of an op amp should be connected to the ground in this case, right. So, we will take one more jumper, the ground is just below that, is not it. So, from the negative terminal we are connecting ground, okay, or we can also connect it at this point too. So, because we already connected this ground using a white jumper wire to this board, right. Now, where do we have to measure output? Where do we have to measure output? Output has to be measured at this particular point. So, by using one more channel of an oscilloscope, the second channel of an oscilloscope, right, it is connected to the output terminal and the negative is connected to ground. So, when we see that, when we see completely from the function generator, we provide supply to the board as an input, and from the from the voltage source we provided plus 15 and minus 15 volts to the operational amplifiers, and one channel of an CRO is connected to the function generator input at the resistor input, right, at the resistor input, whereas other channel is connected to the output. Okay. Now, we will focus on function generator. We will switch on the function generator, we will set input value. So, since in this particular case the threshold values are, so threshold values are plus or minus 1.5 volts. So, what we will do is that we will set a value of somewhere around 2 volts peak. So, we will go to amplitude and we will set the peak value as 4 peak to peak, right. We have set a value as 4 volts peak to peak. We can see the peak value is 2 volts, the negative peak is minus 2 volts. So, this is more than enough for us to visualize it. Now, I will switch on the board. I just switched on the board and I am also switching on CRO. When we switch on the function generator, we can see the signals here. So, what I will do is to just I will change the voltage values times scale, right. Also, what I will do is that I will slightly increase the scale of the input, right, and I see that the scale of the input is 1 volt, whereas the scale of output is 5 volts. That is why, since it is the scale is 5 volts, the box is nothing but 5 volts, 1, 2, 3 boxes. So, why it is not completely 15? The reason is that saturation voltage will be slightly lower than plus VCC value, right. That is the reason it is somewhere around 14, approximately 14 volts, right. Now, what about the cursors? So, we will go to the cursors. I will set a cursors here. So, what is the resistance we have used? 1K and 10K. The gain, the higher threshold value is 1.5 and minus 1.5 is the lower threshold. So, I will take a cursors. It is of amplitude cursor I will take. I am setting amplitude cursor. So, we can see two cursors, one here this yellow and other one this yellow, right. So, what I will do is that I will change the cursors values. So, channel 1 if I see here, I have to make it as 1.5 volts, right. So, I am going to 1.5 slightly, yes, 1.52. Now, channel 2 I will select channel 2, I will go to minus 1.5. Right. Now, is it correct or not? How do you understand whether it is correct or not, whether it is working as per our expected or not? Our expectation was, or as per our theoretical or simulation results, we have seen that when the input voltage, in this case the yellow color sinusoidal input is greater than the higher threshold, in this case plus 1.5, I should get plus VCC, which is nothing but 15. So, now if I see this is my input, this is the higher threshold value. When I observe here, when the input is greater than this higher threshold, the output is gone to plus VCC, isn't it? Meaning the circuit is working as per or expected in the higher threshold. What about in the lower threshold? Look into this. When the input voltage is lower than this yellow line, right, this yellow line which is a lower threshold value, right, it has gone to minus VCC. Everywhere it is following the same thing, right, which means that with the resistance value, the theoretical as well as experimental both are same, right. Here we can see, right, 15 minus 15, but I am not going to do this case in experimental. The reason is that input voltage, when you see, I require input voltage to be greater than 15 volts, but the source it cannot provide more than 10 volts as a peak value. So, that is why I will not consider this, but if you have any source you can also connect this and you can visualize, we can also do the experiment in your labs. Other one is, I will take R1 as 1 kilo, R2 as 2.2 kilo, and in that case the threshold values are minus 6.818 and 6.818, and we will see. Rather than taking the second case, we will go to the third case directly. Now, we will replace R2 resistor as R2 resistor with 2.2 kilo ohms. Previously it was 10 kilo, we will replace with 2.2 kilo. When we look into the board, which is R2 in this case, which is R2? R2 is this one, right, this is the feedback resistor. So, we switch off the power supply and we are replacing this with 2.2 kilo ohms. Right. So, now we replace the feedback resistor with 2.2 kilo. Remaining circuit remains same, I am not even changing any point, then switch it on. But what about the input voltage? The input voltage previously we have set at, when we look into the function generator, the peak value, when we look into this function generator, the peak value is 2 volts, right. Yeah, now this value is 2 volts. Now, I will change the value to more than 7 volts. So, I will be connecting plus or minus or peak to peak as 15 volts or 20 volts, anything is fine. So, we are connecting peak to peak as 15 volts, right. Now, what should be my output? Before looking into the CRO, we will understand how the output should look like. When the input value is greater than 6.8, I should get plus VCC, and again when the input value is lower than minus 6.8, I should get minus VCC. Now, so we are connecting the input to the system, to the circuit at the respected place. Now, when we look into the output in the CRO, so when we focus on the CRO, we can see here, now the input box is also 5 volts, output box is also 5 volts. Now, what we are doing is, we will place the cursors, the both higher threshold cursor, lower threshold cursor to their respective places. In this case, the value is 6.8. So, I will see whether I can exactly place at 6.8, if not approximately near that value. Yes, this is, yeah, okay, yeah, 6.8, right. Again, I will make the lower cursor is also at minus 6.8. right. So, both the cursors, the higher cursor, lower cursor are connected. Now, is it switching on when the input is greater than plus VCC, or sorry, when the input is greater than 6.8 higher threshold value? Why do not we check? See the yellow line, this is our higher threshold, this is lower threshold, this is the input voltage. Now, when the input is greater than this particular value, observe here, this value, it has gone to plus VCC, right. again when the input is smaller than lower than the minus VTL, right, it has gone to minus VCC. So, it is following the same everywhere. So, that means whatever the result that we theoretically obtain for different resistance values, also in using the simulation whatever we have seen, even it is matching with our experimental values too. But when you compare with a normal comparator, in these cases we are by using two resistors we are providing two threshold values, higher threshold and lower threshold values, and the threshold values entirely depends upon your R1 and R2 and what type of circuit that you are doing or where you are applying the input voltage, whether applying it to the inverting terminal or non-inverting terminal. But in realistic way, how do we understand, where do we use this particular circuit? So, why do not you consider the same example we have discussed? Consider a water heater, right. So, day to day life we will always use the water heater. Now, when I see I want to switch on the water heater only when the temperature is lower than 50 degree, but when the water temperature is greater than 50 degrees, sorry, greater than 70 degrees, I have to switch it off. See, understand the scenario, when the temperature is greater than 70, sorry, when the temperature is greater than 70, the output should be low, but when the temperature is lower than 50, then the system should switch on. If I want to design using a comparator, it is not possible. With a comparator I can only put either one threshold, either at 50 or at 70. So, when the temperature, if it is a comparator, if I set it at 70, when the input is temperature is greater than 70, then switch on, input temperature is lower than 70, then it will switch on, sorry, lower than 70 it will switch on, if it is greater than 70 it will switch off. But in this case it is not like that. When the temperature is lower than 50 degrees, then the heater will switch on, and the temperature is greater than 70, the heater switch off. So, there is a time, there is a lag between switching on and switching off your sensor, your heater. So, such a cases are in case of on off controlling. So, that is why the Schmitt triggers are also called on off kind of controller. Such cases wherever you require some kind of hysteresis, some lag between when to switch on, when to switch off, this type of Schmitt triggers can be really useful, right. I hope you understood the difference between inverting as well as non-inverting and how it can be used in practical applications. So, we will see another example, another experiment in our next session. Thank you.